Okay, for the rest of the semester, we'll be spending time on electric circuits. Okay, the last part of electricity that we're going to cover. All right, electrical energy. It's used everywhere. Everywhere you look around, electric energy is being used to power something. Okay, here's an example of a MP3 device. Okay, MP3 player. Okay, where you've got a energy source and you got an energy consuming device. Electrical energy is being transferred from the energy source to the energy consuming device. And the way this is done is, what's the energy source? It's the battery pack, okay? Via electric circuit, conducting wires. It's transferred to the energy consuming device, which is the MP3 player, okay? In the battery pack, in the energy source, you got a chemical reaction that takes place, okay, where electrons are transferred. The charges move via the conducting wires, okay, right over into the energy consuming device. So that's basically how electrical energy is transferred. Okay, here's an example. Here's a battery, okay? You got a positive and you get a negative charge on a battery. The max difference between the terminals, between the positive and negative terminal, is called the electromotive force, commonly referred to as voltage. Okay, voltage is the max potential difference. So there you got a car battery. There you got a common C battery. Positive terminal, negative terminal is a metallic bottom surface. Okay, so, and the notation for a battery. Notation for a battery, you can see it there. It's a long line with a positive and a thicker line with a negative. That's how you represent a battery in an electric circuit diagram. Okay. Okay. Because of these plus and minus charges, that's why electric potential difference exists, is because of these plus and minus charges. Okay. Like I said, voltage, you got 12-volt battery, 1.5-volt flashlight batteries. Okay, now you got electric current. Okay, and what electric current is it's the flow of a charge through an electric field. Okay, the amount of charge per unit of time that passes through a surface that's perpendicular to the motion of the charges. Like I said, it's the flow of charge through an electric field. It's basically equal to the change in the charge divided by the change in the time. Units are 1 coulomb per second is an amp. Okay, so electric current is expressed in amps. Okay, you get two types of, we talked about conventional flow. Flows from the positive to the negative, all right? Electromotive force, potential difference between the terminals of a battery, terminals of a generator, voltage. Electric current, like I just said, is the rate of flow of the charge. If you have constant flow, okay, electric current I is the change in charge divided by the change in time. Coulombs per second is equal to an amp. Okay, there it is. If you don't have constant flow, same equation, I is just the average current flow instead of constant flow. That's the only difference. Okay, you get two types of current. You get direct current and you get alternating current. DC current, AC current. DC current, the charge moves around the circuit in the same direction at all times. It's moving just one way. Okay, charge moves around the circuit in the same direction at all times. Same direction, all times. Alternating current, it's moving back and forth. Moving one way, then it's moving the opposite way. Example of devices that use direct current are batteries, is a good example. Devices that use alternating current, you got generators, you got microphones, you'll see more and more devices use alternating current as we go through the chapter on circuits here. Okay, here's an example. Here's an example. You got a pocket calculator. Pocket calculator, okay, current in a 3-volt battery. I mean, that means you have two 1.5 volt batteries in there equals 3 volt, okay? Is 0.17 milliamps. Don't forget, milliamps, okay? Milli is 10 to the minus 3. So 0.17 milliamps is 0.17 times 10 to the minus 3 amps of current, okay? In 1 hour of operation, 1 hour, okay, what's that? 3,600 seconds, okay? How much charge flows in the circuit? How much energy does the battery deliver to the calculator circuit, okay? How much charge? Current is equal to the change in charge divided by the time, okay? So the charge, how much charge flows in the circuit is equal to the current times the change in time. Current is 0.17 times 10 to the minus 3rd amps, 3,600 seconds. 0.61 coulombs of charge flows in the circuit. Okay, now how much energy does the battery deliver to the circuit? Okay, remember from chapter 19 where the voltage, where you got voltage is equal to the energy divided by the charge. The energy is the electric potential energy divided by the charge, Q sub 0. Okay, so now we want to find the energy. So the energy is going to be equal to the charge times the voltage, Q times V. Q, 0.61 coulombs, voltage, 3 volts. 1.8 joules of energy is delivered to the calculator circuit. The battery delivers 1.8 joules of energy to the calculator circuit. Okay. Okay, when we talk about current, there's DC current, alternating current. Okay, we talk about current. Okay, here's a electric circuit diagram. Okay, where you have your battery, and you have a energy consuming device. There's a device. Okay, current flows. Current flows I. It's flowing basically. It's flowing basically from higher potential to lower potential. Higher potential is positive. The current just generally flows from a positive, even though the conventional current is expressed as it's a hypothetical flow of these positive charges, even though it's actually taking place with the negative charges. It has the same effect. So you show current flowing from the positive charge of the battery. Okay, conventional current. Okay, that's some basics on current and electromotive force. Okay, now we talk about Ohm's Law. Basically, Ohm's Law defines electrical resistance in terms of voltage and current. Okay, here's a battery. Here's a flashlight. Here's a flashlight. Here's an electric circuit diagram where here's the two 1.5 volt batteries in the flashlight. There's the energy consuming device offering resistance. There's the notation for resistance. Notice it's a bunch of jaggedy lines going up and down. Okay, and there's the switch. Turns the flashlight on, turns the flashlight off. The actual resistance in the flashlight is caused by that little filament up there. Okay, so again, note the flow of the current. The flow of I, again, going from the positive terminal of the battery. Okay, that's resistance. It's basically defined, it's a constant. It's a voltage across a piece of material applied to the current through the material. Ohm's Law. Ohm's Law. Voltage divided by current. It's constant. Voltage applied across a piece of material, and I is the current through the material. R is the resistance of the piece of material. In this case, it's the bulb filament. Okay, Ohm's Law. Even though it says Ohm's Law, okay, it's not a law. It's basically a statement. Ohm's Law is a statement about the ratio of the voltage to the current. The units for resistance voltage are ohms. A volt divided by amp is equal to an ohm. So that's the units of resistance. Okay, just take a look at this again. Like I said, Ohm's law, the constant resistance of the material, V is the voltage, I is the current. You also can express Ohm's law as voltage is equal to IR. V is equal to IR, R is equal to VI. Same way. And notation for resistance is a bunch of lines going up and down. Okay, that's notation in electric circuit diagram for resistance. Okay. Like I said here, to the extent that the wire, you got resistance and you got resistor. Okay, they're going to be used interchangeably, pretty much. The extent that a wire or an electrical device offers resistance, that's called the resistor. Okay, the bulb filament is the resistor here. The filament in the light bulb is the resistor in the form of a thin piece of wire. The wire becomes hot enough to emit light because of the current in it. When you hit the switch on, okay, the wire becomes hot enough because of the current in it. It turns the bulb on. The flashlight uses two 1.5 volt batteries, 3 volts, and provides a current of 0.4 amps in the filament. Determine the resistance of the glowing filament. Note the electric circuit diagram. You got a switch. You got a battery, two 1.5 volt batteries. And you got a energy consuming device that's offering resistance of the bulb filament. So the resistance of the glowing filament, okay, is V divided by I. 3 volts divided by 0.4 amps, or 7.5 ohms. That's basically Ohm's law. Okay, we talked about current, and we talked about I, and we talked about R. You're already familiar with voltage. Let's look at a couple example problems here at the end of the chapter. Okay, problem number 6 at the end of the chapter. Here's a car battery. Okay, car battery has a rating of 220 amp hours. Rating is one indication of total charge that a battery can provide to a circuit before it fails. What's the total charge in coulombs that this battery can provide? Okay, battery has a rating of 220 amp hours. Okay, the general format for the current equation, just take a look at this. Okay, is I divided by the charge divided by the time. Okay, the charge would be equal to I times the time. Okay, it would be equal to the charge. Note, in units of current are amps. Units of time are seconds or hours. So basically what you have here, is 220 amp hours. You basically have the I times T part of I is equal to delta Q divided by T. So I times T, 220 amps, is really the change in charge. So what's the total charge that this battery can provide? All you got to do is the proper units of charge are coulombs. Coulombs are an amp per second. So all you basically got to do is multiply that 220 times 3,600 seconds in an hour, and that gives you 7.92 times 10 to the 5th coulombs. That's the total charge that this battery can provide. Pretty simple. Okay, what's the max current that the battery can provide for 38 minutes? Okay, again, current. Current's I. I is equal to delta Q divided by the time. Delta Q is 220 amp hours. Time, 38 minutes. You got to convert that to hours. 38 minutes is 0.633 hours. So what you have is 220 divided by 0.633. You've got 350 amps is the max current that the battery can provide for 38 minutes. Watch your units. Again, like I always say, watch them units. Okay? Let's look at one more example here. Let's look at number 7. You got a resistor that's connected across the terminals of a 9-volt battery. And it delivers 1.1 times 10 to the 5th energy to the resistor in 6 hours. What's the resistance of the resistor? Okay, so you want to look at what's the resistance of the resistor. You want to find R. Okay, Ohm's law, Ohm's statement. R is equal to the voltage divided by the current. Well, you know the voltage, 9-volt battery. Okay, current. Don't know anything about the current, do I? Okay, but I know current is equal to the change in charge divided by the change in time. I is equal to delta Q divided by T, right? Okay, so I could change my denominator to delta Q divided by delta T. Okay, which now delta Q. I don't know anything about the charge here, do I? I know something about energy. Okay, remember like I just said, that the voltage. That voltage is equal to the electric potential energy divided by the charge. So the charge would be equal to the electric potential energy divided by the voltage. Okay? So I substitute that in the denominator for Q. Then I'm left with the resistance of the resistor is equal to the voltage squared times the change in time divided by the electric potential energy. So voltage is 9 volts, change in time is 6 hours. I've got to convert that to seconds. So 6 hours times 3,600 seconds. My denominator is the electric potential energy, 1.1 times 10 to the 5th joules. So the resistance of the resistor is going to be 16 ohms. Okay. Those are 2 good example problems. Do the homework, okay, and we'll continue on with chapter 20 on Thursday. I'll have another taped lecture for the next section of chapter 20. Have a good day. Thank you. Bye.